So first, I'll talk a little bit about why we use numerical models for hydraulic simulation, and then I'll do kind of a little tour of the RAS interface and how to set it up for ice modeling. I'll walk through modeling both an ice-covered river, so unbroken ice, and then an ice jam option as well that uses the force balance equations that Jeremy just went over. So before we go any further, let's just address a basic question: why use a numerical model at all to simulate ice-affected hydraulics? Discussed yesterday in the modeling overview presentation, and there's been a little bit of discussion about it today. There's different options for modeling ice depending on what you're trying to accomplish by using a model at all. So with numerical hydraulic models, at least ones that we're interested in using for modeling cold regions, river systems, they simulate the physical processes that dictate how the water flows in an open channel. So we specify the geometry and the roughness of the channel. We specify a flow rate, or in general, provides boundary conditions for the model. And then the model uses physics-based equations that do things like conserve mass and conserve energy, and they predict how that system that we just set up in the model behaves. So from the results of that model, we can directly see estimates of things like stages and velocities and that sort of thing. So this is all kind of obvious, but it's important, I think, sometimes to just step back and think about what we're trying to do when we use a model. There are tools that we use when we need that level of specific information in planning applications, like was been discussed, looking at FEMA flood elevations and that sort of thing. We use them to design things like revetments and levees, and where the stage elevations are important for those. And we use them to compare design options as well, to be able to quantitatively show the difference between one design or another, or a do-nothing approach versus a build-a-project approach. And we also use models routinely in operational capacity. What happens to stages downstream if we release water from a dam, and what are the impacts going to be? So they're important decision-making tools as well. So probably preaching to the choir a little bit on this, but when we're using a numerical model, we should understand what we're trying to do, obviously. So we've covered why a little bit. So let's actually look at one of the modeling options. So we've been talking a lot about HEC RAS. That's because I work for USACE, and this is the software that most of the districts use, and it's pretty nice software in my opinion. And the other benefits of it is that it's free to download, free to use. If you want to grab a copy yourself, you can go and use this link, or just search for HEC and download the current version, which is 6.2 right now. So RAS has both, I'm not going to do a full overview of RAS, but I'll just talk about it at super high level. So it has both 1- and 2-dimensional modeling options, which we've talked about today. In 1D, the reaches are modeled with cross sections that run perpendicular to the flow. And then all the flow is assumed to move from one cross section to the next cross section, more or less perpendicular to those cross sections. So it's one-dimensional flow; it's moving in one direction. And then this is an assumption that's reasonable for a lot of river systems, where the majority of the flow is moving parallel to the channel center line. It doesn't work everywhere, of course. For more complex flows, particularly where out-of-bank flows are common, or there are channels that have lots of different flow paths, like a braided river system, for example, 2D models are really useful. So the 2D model operates on a mesh, and the flow can move any direction any direction in a horizontal plane. But in RAS, it's 2-dimensional. There's no vertical velocity. It's depth average. So that's why it's called 2D. Ice covers and ice jams can only be modeled in the 1D module now. I mentioned that a few times. We'd love to have it in 2D, and hopefully we'll get there at some point. But right now, it's only in 1D. In ice covers, they're run in steady. You can run on steady and unsteady flows with an ice cover, meaning you can vary the flow, or it can just be a constant flow. The ice jam routine, though, that only works in steady flow conditions. So it's just a constant flow rate being run through the model for those. So for those of you that aren't familiar with RAS, this is the basic interface, some shortcut buttons for the common workflow tasks, setting up the geometry and input data, running the simulations, viewing the results. So the first step in building a model is to set up the inputs. So I'll show you some of these in more detail in a minute, but there's a geometry editor where we can set up and edit our river system. There's steady and unsteady flow data editors where we can specify how much flow we want to put through the system. There are other options to specify what's called a plan in the language of RAS, where you combine a geometry information and flow data and create a simulation run. So step through some of that here in a minute. There's actually a bunch of ways to review the results depending on what you're interested in. There's a RAS mapper, which is kind of like a GIS type environment. Touch on that here in a sec. The more classic outputs are cross-sectional views, profile plots, where you can see the stage and energy grade lines along the whole stream length. There's some options for viewing rating curves, looking at hydrographs. RAS writes all the results out to a format called DSS, so you can view results in kind of tabular form there, but there's also some tabular outputs within the RAS application as well that you can look at your results at. So to start a model, we need a representation of the geometry, and that's what the geometry editor is there for. We specify and edit the location of the river channel, edit the cross sections, and we'll see in a minute, this is where most of the ice data goes in. Let's flip over to the RAS mapper. This is kind of a newer implementation in RAS. It's a light sort of GIS environment. So for anybody that's familiar with ArcMap or QGIS, it's a lightweight version of a GIS application that's tailored to help us set up RAS models and view the results. So there's layers on the menu to the left where you can turn on your geometry, your cross sections, and then there's also the ability to look at spatial representations of your results, like your stage or velocity information. So we can overlay imagery, or you can actually bring in any sort of raster or shapefile you want to. So this is actually a really neat tool for viewing information, spatial information, along with your model results. So this interface is kind of used in tandem with the geometry editor now. I think they're going to eventually move everything over into RAS mapper, but right now we're kind of have to flip back and forth. But it's actually pretty convenient to specify a lot of the geometry right in RAS mapper and extract elevations from a DEM, even specify things like roughness from a raster based on land cover. You can do all that in RAS mapper. So it's pretty handy. So just flipping back now to the geometry editor. This is the cross-section editor where the station and elevations are specified over there in the columns to the left here. We specify the roughness values for the bed and for the channel in both the overbank. So the channel location is obviously the center of the river, and that's defined using these bank stations here. And the default is just a left overbank, a channel, and a right overbank. You can add more zones if you want, if you've got more complex cross-sectional area you want to model. There's a few other things you can specify here, but I think we've gotten through the basics here, so I'll just keep going along. So we want to use this model to simulate ice-affected conditions. So we specify the ice using the geometry data window again. The main inputs for modeling ice, affected flow in RAS, and we're not talking about ice chains yet. We're just talking about ice on flow that's unbroken. Those inputs are the ice thickness and the ice roughness. We can do all that through the cross-section editor as one option. So we can opt to specify, so we do, there's just got to select the menu here. So it's just showing you where the menu is to add ice cover. Oops, going the wrong direction. There we go. And this is the input window basically for ice cover at a cross section. And we specify the ice thickness and the roughness on those that top row. If we wanted, we could edit the density of the ice, but that's something we only do if we have some specific reason to do that. If you're trying to model sea ice, for example, so usually we just leave that be. And then this is actually the place where we set up the ice jam parameters, but we'll come back to that when we actually talk about ice jams. So that's nice if you can do that through the cross sections, but as anybody who's run a model of a river, there's a lot of cross sections, so it's kind of tedious to put in all that data at each cross section. So there's a way to do that in a bulk sense from a table. So that's an option where you can specify ice thickness and roughness for a whole range of cross sections. Okay, so we've got the geometry set up. Now we can go and specify flow rates and boundary conditions. This is a steady state model, so we'll use the steady state flow editor. This screen here is where we specify the flow rates for the simulation. You can see that this one actually has flow specified at a few different locations on the river. So that's what each of the rows are, is different locations that we're specifying flow. And there's actually 3 different scenarios here that are being run: a 10-year flow, a 50-year flow, and a 100-year flow. So we can specify different combinations or different scenarios here. And we also specify the boundary conditions in a sub-menu here. We'll skip going into that for now, but you can use like a known water surface elevation or a rating curve for downstream end of the model. There's a few different options there. So now we've got geometry, we've got flow. It's time to actually run the model. So to run the model, we have to specify a plan. We do that through the steady flow editor. In this case, since we're doing a steady model, and we do that just by combining the geometry file with our flow file. So you can see we select those here with this menu. This is actually pretty cool because we can reuse the same geometry file with different flow files, or vice versa. We could use different geometry files. We could have like a pre-project geometry and a post-project geometry, or an ice cover, no ice cover scenario, and still use the same flow file. So it makes it a little more convenient to do it this way. So in this example, we have an open water plan that's being run. You can see that in the plan name. And so the geometry and the steady flow, or the geometry and the flow files are tied together with the plan file. So in this case, we'll just hit the compute button, and that'll kick off the model. And this is just the progress bar. It'll tell you if there's errors in your model. Hopefully you get the blue bars and everything's good. And so then we can go and actually look at the results. We look at the results of, well, in this case, we're showing the profile, so profile view, and we're seeing the results of 2 different plans overlaid on each other here. So I just oriented the water's flowing from the right to the left. The kind of jagged line at the bottom, that's the channel bottom, obviously. The solid blue area is the open water result, and then the little blue hatch line that's kind of floating above in the air above the water there, that's the ice affected simulation. So you can kind of toggle the colors and the fill and stuff depending on what you want to do. This is just sort of the default to make it look a little less busy when you're comparing plots. But what this shows is that for the same flow rate, so we use the same flow file, and this is looking at the same specific flow case, but with ice and without ice, we see that the ice affected stage was a bit higher than the open water flow. So you might recall earlier today when I was talking about open channel hydraulics, said that there's this rule of thumb that ice affected stage could be around 23% higher than the unaffected. And that definitely doesn't look like what we're seeing here. So what's going on? This particular example is from the Pend Oreille River in Idaho, which Jeremy mentioned in one of the earlier talks, I think yesterday. And this particular reach is affected by a dam downstream. So a lot of this river is in partial backwater. So the velocities are kind of unusually low. So the impact of ice on stage is actually a little bit muted here. So this is a one benefit of setting up and running a model like this. We can account for kind of complex phenomena and not rely just on simplistic assumptions. So this is just another results view from the same model. In this case, this is just an example of border ice growth. So we've got kind of a way that we can model border ice on the sides and then open water in the middle, and have an estimate of the impact of an incomplete ice cover on the river stage. And if anybody wants to do this, this isn't really something you do totally easily out of the box with RAS. We've developed some methods to do that here at CREL. So if somebody wants to do that, feel free to reach out to us, and I can kind of point you at some publication we have on that. And then, yeah, I think we'll just keep going here. So that was the ice-affected part of this presentation. So now I'll talk about modeling ice jams. So I won't go back into the force balance derivation that Jeremy walked us through, but just recall some of those terms. The key ones we'll use to set up our model are the angle of internal friction, the density of ice, the porosity of the jam. So that's the porosity of the kind of granular material we're assuming the jam is made out of. And then K1, which is the ratio of lateral to longitudinal stress. So we won't dive into the math again, like I promised, but this is the force balance here, and this is what RAS uses to solve the force balance. So all those parameters I just mentioned, they get entered into each cross-section. We can use the individual cross-section editor if we want to do that, but RAS does provide default values, which is great. It's a good place to start. So you don't have to kind of manually type all this stuff in if you don't want to do a quick run, but you should make sure that the values that you're using make sense for your application at hand. So we'll skip the mean velocity under the ice curve for just a second. But yeah, this is mainly talking about the inputs to the jam. So just like specifying ice cover and roughness, it's often easier to use the tabular input to put in this data. So that's the option here. If you recall, on 2 slides ago, there was a little checkbox at the bottom where we could select whether to use a fixed roughness or use something called Nezhakovsky's formula. So the under ice roughness of a jam has been shown to vary by both the thickness of the jam and the depth of the flow. And this is represented with the 2 formulas that I have on the screen here. But since the jam routine will be solving for the ice thickness, and that'll of course have an impact on the depth of the flow, makes it kind of tricky to estimate these up front. So RAS is actually set up to adjust the roughness value as part of the iterative solution, so that when a solution is found, that these equations are satisfied. So it kind of takes us out of the iteration loop in terms of specifying an under ice roughness for the jam. So if you do feel particularly strongly about using a certain roughness that you really like, you can specify it if you want. You can turn off or you can actually check the box, and that will allow you to use whatever you specified as the jam or as the roughness. So here is the tabular entry where we can flip on or off ice jamming for certain reaches of the river. The user can just specify, or the user has to actually specify where the potential jam will occur. And this needs to be, it needs to be a cross-section of intact ice upstream of where you're initiating the jam to allow the force balance routine to initialize correctly. So the last thing to consider before actually going and running the simulation is this concept of under ice velocity. Jeremy talked about this a little bit. So in the force balance derivation, we mentioned that there's this assumption of buoyancy of the ice, so we can't simulate a grounded jam right now. With this method, we have to assume that the jam is floating. So to ensure that the calculations don't allow the ice thickness to grow so much that it will get to the point where it will touch the bed, that can happen if we don't actually restrict the velocity of water under the jam. Okay. So to do that, we'll start just quickly. So from continuity, the flow. Just remember Q equals VA, so the flow equals the velocity times the area. So the velocity is equal to the flow rate divided by the area of flow under the ice jam. So that's the area under the ice jam is the channel width, and that's multiplied by the distance between the bottom of the jam and the bed. So as the jam gets thicker, the value of D will tend to get smaller, and if there was no restriction, it would eventually approach 0. And then you can see that V could get unreasonably or totally unrealistically high. So if we set a max velocity, we ensure that D can't approach 0. So this value is something the user should make sure makes sense. For your particular system, the default's 5 feet per second. Note that increasing the the value here for the maximum velocity will tend to allow the jam to become thicker. And this is where that value is input in at least the cross-section editor. And then same thing for the tabular input. So running a jam is just like running an ice-affected simulation as long as the geometry is set up with the ice jam parameters specified. So we'll set up the plan using the geometry file that has the ice jam data specified in it. So that data is tied to the geometry. So if you want to run an ice cover and a ice jam simulation, you need different geometry files, to account for that. And then we run the simulation just the same as before. You can see there's a little indicator here that the arrow is pointing to, where that tells you how many iterations the jam solution or the algorithm's gone through, along with the step back water solver. So we can review review the results in the same way as the ice affected or open water results. So here we have the same run with an intact ice cover and one with an ice jam. And you can see that in this case, there's a few feet of difference between the stages. So one thing to mention on this slide, because I think it's a good visual, is that RAS does not conserve ice volume. So the user needs to make sure that the volume of ice in the simulation, or that the simulation calculates in order to satisfy the force balance equation, is actually available from an ice run coming from downstream. So for big river systems, that might not be much of a constraint, but for small river systems or somewhere there's a limit to the amount of ice that's available to run upstream, the jam routine could violate that limitation. So that's just something to keep in mind. And here we see that this is the same results, but in a cross-section view is a little less exciting than the profile view. But you can see that the jam is thicker than the no jam case. And then this is just another example of a useful plot. This is a velocity, channel velocity, the average velocity each section. So that you can compare the ice versus ice jam versus open water velocity, if that's something you're interested in. And then finally, we've got some tabular output. There's lots of hydraulic variables that RAS calculates for each time step. We've got flow rate, water surface elevations, and velocities and stuff. There's a lot more of other stuff you can kind of dig into if you're interested. And so you can export these to Excel and make some plots or whatever if you wanted to, or like I said, they're exported to a DSS database format, and that allows them to be used directly in other HEC applications, or you can pull them into some other process using a script or something like that. It's a pretty handy data format. In this table here, this shows some ice-specific data, including the ice thicknesses, and the total. What's interesting here too is the total ice volume. That's a cumulative summation. So this table is really useful for doing that check I just mentioned in terms of conserving ice. So yeah, I think we'll just keep going here. Okay, yeah. So this is just a brief overview of RAS with ice. There's more information in the RAS manuals. They're actually pretty well done with respect to ice. There's a nice write-up on the ice jam routine if you want to get a little more into the details. And I'll just say that once the 1D model's set up, takes a little bit of time to get one set up. It's pretty quick to run. It's a pretty efficient solver. So it's pretty easy to change variables and see what the impacts of your changes are. So if you're going to get in there and use it, don't be afraid to mess around with it and break it, because it's pretty fast to run and experiment with. So with that, I will take any questions. I know it's the end of the day, but I'll stick around if folks have questions for sure.